What happens when artificial intelligence demands more electricity than the grid can deliver? AI looks weightless, a prompt goes in, an answer appears, nothing seems to move. But behind that answer is an industrial machine made of steel, copper, cooling water, transformers, turbines, and hundreds of billions of dollars. In 2025, electricity consumption at AI-focused data centers increased by roughly 50%, according to the International Energy Agency, and the race is accelerating. The answer to that opening question will decide where the next hundreds of billions are spent, which regions win the AI boom, and whether ordinary consumers help pay for it. The companies building the world's most powerful intelligence have spent years fighting for chips. Now they are discovering a different constraint. You can order more servers, you can raise more capital, but you cannot instantly build a power plant, a transmission line, or a high-voltage transformer. AI's next crisis may not be a shortage of intelligence. It may be a shortage of power. For most of the internet era, software companies appeared to escape the limits of the physical world. Their products could reach another million customers without building another million stores. Their most valuable assets were code, data, and networks. AI changes the scale of that bargain. The IEA says capital expenditure by 5 major technology companies exceeded $400 billion in 2025 and was expected to rise by another 75% in 2026. Not all of that money is going into AI, but enough is flowing into data centers, chips, networks, and power infrastructure to reshape entire regions. Microsoft's Fairwater AI campus in Wisconsin makes the scale tangible. The company says the site covers 315 acres. Its 3 main buildings contain about 1.2 million square feet. Construction required more than 26 million pounds of structural steel, 120 miles of medium-voltage cable, and over 72 miles of mechanical piping. That is not an app. It is a factory. And factories need power. A conventional data center runs many separate jobs: websites, databases, email, video, and business software. Frontier AI can behave more like one enormous machine. Thousands of specialized processors work together, exchanging data at extreme speed. The closer and more tightly connected they are, the faster they can train or run a model. That concentrates enormous computing power into each rack. Between 2020 and 2025, the power density of AI servers increased 11-fold, according to the IEA. By 2027, it could rise another 4 times. At peak demand, one advanced rack could draw as much power as 65 households. And the problem is not only how much energy it consumes over a year. It is how much power it needs at a particular second. AI training can cause thousands of processors to accelerate and pause together. Those coordinated swings can create a new class of stress for the electrical system. So an AI factory needs more than servers. It needs heavy electrical connections, advanced cooling, backup systems, storage, and equipment capable of controlling rapid changes in demand. Every breakthrough in computing creates another engineering problem outside the computer. The real bottleneck appears when 2 clocks collide. Clock 1 is technology. A large data center can move from plan to operation in roughly 2 or 3 years. Hardware generations move even faster. Capital can be approved in a quarterly board meeting. Clock 2 is energy. New transmission corridors, power plants, substations, turbines, and transformers can require years of engineering, permits, manufacturing, and public negotiation. And electricity is not interchangeable across a map. A country may produce enough power in total, while a specific region lacks the local generation, transmission capacity, or grid connection required by a new campus. The request is not simply, "Give us electricity." It is, "Give us a huge amount, at this exact location, at high reliability, potentially every hour of the year, and have it ready before the next generation of chips becomes old." That is why project announcements can be misleading. A proposed campus is not an operating campus. A requested grid connection is not delivered electricity. And a pipeline containing several competing projects may exaggerate the demand that will actually be built. But the pressure is already visible. The IEA says supply chains have tightened for transformers, gas turbines, power electronics, advanced chips, and other critical equipment. Regulators and grid operators are being asked to plan infrastructure for demand that is enormous, fast-moving, and uncertain. AI may advance in months. The grid advances in steel. When electricity becomes strategic, technology companies start behaving like energy companies. Google has worked with Kairos Power and the Tennessee Valley Authority on an advanced nuclear project designed to deliver an initial 50 megawatts to the regional grid beginning around 2030. The wider Google and Kairos framework targets as much as 500 megawatts across multiple deployments. Microsoft signed a 20-year power agreement connected to restarting a nuclear unit in Pennsylvania, now called the Crane Clean Energy Center. If completed, the project is expected to return 835 megawatts of carbon-free capacity to the grid, potentially as early as 2027. Amazon is supporting existing nuclear generation, small modular reactor development, batteries, and renewable projects. These are not charitable side projects. Reliable energy is becoming part of the competitive mode. But nuclear power is not a fast universal answer. New designs still face financing, permitting, construction, fuel, and schedule risk. That is why developers are pursuing almost everything at once. In some constrained U.S. markets, proposed AI campuses are considering on-site natural gas generation. The IEA estimates that reliably serving a critical and variable data center load with on-site gas can require building 30 to 70% more generation capacity than the nominal demand. Batteries can respond quickly to fluctuations but cannot create energy. Renewables can add large amounts of electricity but require transmission, balancing, storage, or firm backup. Demand response can temporarily shift computing to support the grid, but not every workload can wait. The likely answer is not one technology. It is an expensive portfolio. Grid expansion, generation, storage, flexibility, and efficiency, all built together. During a gold rush, the safest fortunes are sometimes made by selling the tools. The AI boom has already rewarded chip designers and server manufacturers. The power bottleneck expands the list. Transformers, switchgear, cooling systems, high-voltage cable, turbines, batteries, engineering firms, construction companies, utilities, land near power and fiber. The value chain extends from the silicon inside a rack to the steel tower carrying electricity across a state. But scarcity does not guarantee easy profits. Factories take time to expand. Utilities operate under different regulatory systems. Projects can be canceled. Communities can reject new construction. A component that is scarce today can become oversupplied when investment arrives all at once. And somebody must pay. A large data center can add jobs, tax revenue, infrastructure, and long-term demand. It can also require new generation and grid investment while using land and water and concentrating risk in one location. Whether local customers benefit or face higher costs depends on the contract, the regulation, spare capacity, and who carries the risk if an announced project never reaches full operation. That argument has now reached national policy. In July 2026, more than 200 American utilities, data center developers, cooperatives, and state governments joined an expanded ratepayer protection pledge. Its principle is simple. The companies creating the demand should fund the new power supply and grid infrastructure required to serve it. The pledge is voluntary, and the real test will be contracts, regulation, and enforcement. But its existence reveals how quickly AI infrastructure has moved from a technology story into a household cost and political story. The IEA's conclusion is careful. data centers do not inevitably increase electricity prices. In a system with spare capacity, predictable demand can improve utilization. In a constrained system, badly planned growth can shift costs onto everyone else. The bottleneck is not only technical, it is financial and political. There is one powerful argument against an energy crisis. AI is becoming far more efficient. The IEA says the electricity required for a simple AI task has been falling at an extraordinary pace, by at least an order of magnitude each year in recent periods. A basic text query can require less energy than running a television for the same amount of time. That matters. Better chips, software, cooling, and data center design can produce far more intelligence from every watt. But efficiency per task is not the same as lower total demand. When a service becomes cheaper, faster, and more capable, people use more of it. Simple chat expands into reasoning, autonomous agents, video generation, scientific simulation, and always-on systems. Some of those workloads can consume hundreds or thousands of times more energy than basic text generation. So two things can be true at once. AI can become radically more efficient, and the industry can still consume more electricity. The ultimate outcome remains uncertain. If adoption slows, models stop improving, or companies fail to convert infrastructure into revenue, today's project pipeline could become a historic overbuild. If AI becomes embedded in transport, medicine, manufacturing, entertainment, and everyday work, the current forecasts may prove conservative. The power system must prepare before anyone knows which future arrives. For a decade, the AI race was described as a contest for talent, data, and chips. Now it is becoming a contest for substation, transformers, turbines, cooling, storage, transmission, and public trust. The companies with the best algorithms will still matter. But the winners may also be the ones that can secure reliable power, build without shifting unacceptable costs to their neighbors, and turn enormous physical investment into useful intelligence. AI's future may be written in code, but it will be built in copper, concrete, water, and watts. That is where the billions go. Subscribe to Where Billions Go, evidence-led stories about the machines, money, and power building tomorrow.